everyone. So today I would like to present to you about safety, sustainability and also technical workshop practice of sheet metal. And my name is Nabiha Shafina binti Kamarul Arifin and this is my group member.
My name is Muhammad Arifin bin Muhammad Izani.
Hello, my name is Muhammad Imam Farish bin Muhammad Safi'i.
Hello, my name is Muhammad Kazim Hakim bin Kasrianto.
Did you know sheet metal fabrication is widely used in engineering industries such as aerospace, construction, automotive and also manufacturing. In this workshop practice, several fabrication processes were performed such as marking, cutting, bending, drilling and also repainting. Despite developing technical skills, it also emphasizes safety and sustainable for engineers. To guide our project to the highest standard, 4 core objects were established. The first one is technical. It is to master precision sheet metal fabrication technique according to the engineering drawings. The second is safety. It is to follow the workshop protocols in compliance with Malaysian safety legislation. The third is sustainability. It is to minimize raw materials through optimal banking layers and scrap management. And the fourth is learning relevance to evaluate how engineering technicians directly contribute to efficient, legally compliant and eco-friendly manufacturing environment.
Now, I will talk about safety and sustainability practice. To maintain a safe and sustainable workplace, our team strictly follow 5 engineering practice. First, full PPE compliance was enforced. Under Section 24 of the Occupational Safety and Health Act (OSHA) 1994, employees and students have a statutory duty to wear protective equipment provided. This practice eliminates liquefaction from sharp sheet metal bursts and protect eye from flying metal chips during drilling. Second, we conducted immediate clearing of metal swath using dedicated brushes. In accordance with Regulation 28 of the Factory and Machinery Safety, Health and Welfare, Regulation 1970, all working floor must be kept free from burst material and debris to mitigate slip, trip and puncture hazard. Third, we maintain strict machine boundary zone. This satisfies Section 15 of OSHA 1994, which required the maintenance of a safe working environment, as well as the factory and machinery fencing of Machinery and Safety Regulation 1970, ensuring bystander protection from the dangerous mechanical shear and pinch point. Fourth, for sustainability, we implemented bulk scrap accumulation. Instead of disposing the metal piece by piece, follow me. We put them in the centralized bin. The economic and environmental reason is to optimize recycling logistics, reducing carbon footprint during transit, and significantly lowering overall factory waste handling costs. Fifth, we established a closed-loop scrap recycling workflow. This is because steel and aluminium are 100% recyclable without loss of quality. This practice diverts structural waste from landfill and saves up to 95% of the primary energy required to manufacture virgin raw material.
Despite this protocol, there are 4 critical ethical, safety and sustainable issues that are connect with the problem that we have. Issue number 1, the mix of disposal of sharp scrap into domestic trash and bins, like we see here. So, for the impact of the students, immediate threat of several puncture wounds doing regular trash disposal. Means when students want to dispose trash, just like scrap or sheet metal, they will get a wound. Second, impact on workshop staff. It exposes laboratory and cleaning personnel to hidden hazards while handling generic bags. It means when workshop staff want to dispose the trash, they will cut their hand with the biohazard sharp. Issue number 2 is the noise pollution. So for the impact of the student, They will replicate fatigue, rapid cognitive fatigue, reduce operational focus, and long-term risk of noise, included hearing loss. For the impact of the workshop staff, they will face extreme vocal strain trying to project critical safety instructions. Issue number 3, blanking layout technique, leading to low material utilization. Input on students force them to consume excessive materials, delaying project workflows and stop runs. For the impact on the workshop staff, it causes faculty operational and procurement budgets to spike. Issue number 4 is handling associated with the band health. Impact on students result in immediate exposure to radiation blade causing serious wound. So next, impact on workshop staff, instructor to stop the class to make the first aid emergency first to the student that have wound.
For solution 1, color coded segregation bins. Our action is deploy function of industrial bins solely for porous metal. Justification is eliminate shortcut trades to students and cleaning tools. The compliance is executes clause 8.1 of ISO 14001 for waste control and section 15 of OSHA 1994 for a hazard-free workplace. For solution 2, two-tier acoustic controls. Our action is upgrade the standard of steel hammers to dead blow polyurethane hammers and install high density from acoustic partitions. The compliance is prioritize engineering controls under Malaysian standard MS 1722 and stays below threshold limit under the OSHA noise exposure regulation 2019. For solution 3, computer aided nesting of software. So for the action, we require design software simulations to plan cutting layouts before processing raw sheet metal. And the justification is we optimize material efficiency and reduce physical metal scrap, fulfilling resource conservation goals under ISO 14001. So for solution 4, student-led toolbox talks. Our action is to mandate high visibility warning boards and student safety officer glove checks before entry. And our compliance is satisfies workers' participation under clause 3.2 of MS 1722 and ensures university legal compliance under OSHA 1994 through safe regulation.
As future engineering professionals, we must critically evaluate conflicting project variables such as capital cost, physical safety, and environmental sustainability. Number 1, capital cost versus safety and environment. Purchasing acoustic panel, software license, and polyurethane hammer injects immediate upfront costs into the university budget, tempting fiscal decision maker to reject them. Second one is the hidden risk of financial bleeding. However, rejecting this solution causes long-term financial loss. Ignoring noise hazard leads to student hearing impairment, claims and legal costs, while poor layouts continuously bleed cash to raw metal waste. The third is our practical trade-off solution. Therefore, we propose a phased implementation strategy. The university incurs a low initial cost for nesting software and polyurethane chemicals. This balanced approach satisfies safety costs, minimizes resource waste, and guarantees long-term payback through material savings.
In conclusion, our project successfully bridges technical sheet metal fabrication with industrial compliance framework. Here is our final synthesis and recommendation. The first one is the co-finding. Our synthesis is engineering. Technicians' role extends beyond manual labor. It requires direct responsibility over legal, ethical and ecological workshop standard. Recommendation 1, centralized automated waste monitoring. Action, convert physical scrap storage into a digital tracking system link directly to licensed recycling vendors to establish a verified circular waste economy. Recommendation 2, upgrading grading mechanism. Action, integrate physical safety compliance metrics and material utilization score straight into academic marking rubric.